Hi everybody. This is our lecture on section 4.2, direction fields. And numerical methods. So consider a first order differential equation of the form y equals x fx y. So, or y prime, sorry. Y prime equals fxy. So just one instance of y prime in the equation, and then over here you just have some expression for x and y. In this case, okay, any solution to this differential equation if y equals g of x is a solution to this differential equation, then the slope of y equal g of x at any point x, y is given by y prime equals f x, y, right? I mean, dy dx, or y prime, is the slope of a function at a given point. So if we put little slope indicators of many slope indicators at points x, y in the two-dimensional plane, will yield what's known as a direction field. Right, and solutions to the differential equation will follow the direction field. Is this recording? Yes. Must follow the direction field. Okay, so for example, what are we talking about here? Consider the differential equation y prime equals minus y over x. Okay, let's draw what this direction field looks like. Let's just do the first coordinate, quadrant. Okay, along the line y equals x, right? This is the line y equals x. So when y is equal to x, y prime is negative 1. And the slope of negative 1, right, is 45 degrees in the downward direction from left to right. Right, so it looks like that. Along these points, that's what the slope of a solution looks like. Now, for any line up through here, this is y equal to 2x, say, right, the slope is minus 2. So minus 2 is a steeper slope. So as we go, that's y equals 3x there, right? Slopes here are going to have -2, and slopes here, -3. The larger the slope gets, the more vertical it becomes, right? So slopes get steeper as this angle this way increases. So let's see. Let's draw those two lines again. Like that. So these slopes are -2. So just kind of guessing that's steeper than 45 degrees. These are -3, which are even steeper. This is the line y equals a half x. Slopes are -1/2, which is more flat, right? So I'm not being constant along here. So a half, that's 2. A half, right? It's flatter than 45 degrees. And along here, y equals 1/3 x, even flatter. A third, a third, a third, a third. Right, so this is what the direction field looks like. And you could sort of fill in maybe some other spots. But that's a pretty good idea there of what the direction field looks like. Right, so these are slopes -1, -3, -2, right? Slopes -1, slopes -1/2, slopes -1/3, slopes -2, so on and so forth, right? And you can have however many lines through the origin to represent that. So now a solution to y prime equals minus y over x, a solution y equals g of x to y prime is equal to minus y over x follows this direction field. So if this is the point 1, 1, say, then a solution here would do something like this. Right, flattening out as we get further away from the origin. Steepening up as we get further away from the origin, as the angle between the origin increases. And if this is the point 1, 1, then this is the solution y equals g of x, satisfying particular solution. Y equals g of x, satisfying y of 1 equal to 1. If it goes through the point 1, 1. If you have any other point that you need to be part of the solution, you know, it could be over here, and then that's your solution. Something like that. Yeah? So, well, why don't we do that? So if that's the point 4, 2, say, 4, 2, maybe I could do that in a different color. Y equals g of x, satisfying y of 2 equal to 4. Right? So you can have different particular solutions that go through different points. All right? Let's get another example. how about y prime equals y minus x. Y prime equals y minus x. So where x is equal to 0, which is on the y-axis, the slope is just equal to the y-coordinate. So here's a kind of a flat slope. Here's a slope of 45 degrees, which is 1. Slope of 2. Slope of 3. Slope of 4, even steeper. And then going in this direction, right, a slope of, say, negative a half, a slope of negative 1, a slope of negative 2, negative 3, and negative 4. Right, so now for x equal to 1, right, the slope is y minus x. So what it does is it shifts this guy up 1. Right, here you have a slope of 0 at 1. At y equal to 1, you have a slope of 0. Right, so this is x equal to 1, y equal to 1. And then it goes up from there. Actually, let me copy this over. See how that's going to work. So shifting up 1 unit. And then shifting up 2 units. Right, so you have a slope of 1 at 2, or slope of 0 at 2, which is right here. Slope of 0 at 1, slope of 0 at 2, and then, so on and so forth, moving up the line like that. Actually, let me copy this one that's got that marker. Right, and now erase these verticals. Right, so there's the direction field. Going down even steeper here. Right, like that. And then going in the opposite direction when x is negative. So for x equal to negative 1, we're down here. Negative 2, we're over here. Right, so there's a nice picture of this direction field. Right, this is, oops, I didn't want to erase the y-axis. At the y-axis, okay, so this is the direction field for this one. Basically, okay, we started with what happens when x is equal to 0. And we got these slopes here. 0, a half, 1, 2, 3, 4. Negative a half, negative 1, negative 2, negative 3, negative 4. And then as you move to x equal to 1, it simply has the effect of putting the 0 slope 1 unit up. So I just copied that line of slopes and moved it up 1, to the right 1 and up 1. Right, and then to the left 1 and down 1. And that's a direction field for this differential equation. And so a solution, why don't we do it this way? And here is a solution passing through the point 0, 0, say, would look something like, right, y equals g of x, satisfying y of 0 equal to 0. So solution, particular solution. Okay, so these are direction fields. Conceptually, they're nice, but they do give rise to one method for estimating solutions to differential equations. And, you know, if you can't solve it by other means, you can always estimate. And this is called Euler's method. Okay, so this is a method that approximates some small part of a solution to y prime equals fxy, which takes advantage of the slopes given by this differential equation. Okay, so you start with an initial condition. An initial point, x0, y0. Okay, and then after you have your initial point, well, you start with an initial point 0, 0, 0, and then calculate the next point. x1, y1, and then calculate the next point, x2, y2, calculate the next point, x3, y3, where xi plus 1 is equal to xi plus some delta x. Okay, where delta x is equal to b minus a over n, and yi plus 1, well, what's that going to be? Well, we know the slope, right? It's going to be yi plus the slope f prime xi yi times delta x. Right, so the picture that you get looks like this. Right, there's xi. Here's xi plus 1, and this slope, or this length here, is delta x. And then this length right here is delta y equal to that. F prime xi yi delta x. Actually, I'm not going to put that there. I'm just going to put this here. Okay, so this is the point xi yi, and this is the point up here xi plus 1 yi plus 1, right, where the change in the x-coordinate is delta x, and the change in the y-coordinate is this thing right here, the slope of a solution times delta x, right? So you're moving along this line here. So that'll give you some sort of approximation for small values of delta x in some very tiny interval. But you can't continue it too far because you get, these are only approximations, and the error gets worse and worse as you go along. So, for example, let's go back to that first differential equation. So, for y prime equal to minus y over x, let's pick delta x equal to a half and initial point x0, y0 equal to 1, 1. Okay, let's perform 4 iterations of Euler's method. And compare our results to the actual solution right, y equals 1 over x. Right, y equals 1 over x, it goes through the point 1, 1, and it satisfies this differential equation. Y prime is minus 1 over x squared. Right? Let's check it out real quick. So y prime is minus 1 over x squared. And then minus y over x is equal to minus 1 over x, which is equal to minus 1 over x squared, and these are the same. Right, so that is the actual solution that goes through the point 1, 1. I mean, since we know the actual solution, there's really no point in using Euler's method, but, let's just do it for illustrative purposes. Okay. So starting at the point 1, 1. So here's the point 1, 1. All right. Now that's x equal to 1. That's x1 is 1, x3, x0 is 1, x2 is that plus a half, which is 3 halves. This is x0, and then this is x1, and then x2 is going to be this plus a half, which is 2. X3 is going to be 2 plus a half, which is 5 halves, and then x4 is going to be 3. So that's 3 iterations, 4 iterations. All right. So y1 is 1. y1 equals 1. So, or y0 is equal to 1. So y1 is going to be minus y over x. Let me see. Let's do it this way. So x0, y0 is equal to 1, 1. And then y prime is equal to, well, minus 1 over 1, which is equal to minus 1. So now x1 is equal to 3 halves. And then y1 is equal to, well, y0, which is 1, plus the slope times delta x, which is a half. So 1 minus a half. So that's equal to 1 half. So x1, y1 is equal to 3 halves, 1 half. So here's a half right here. Joining these 2 points by a straight line gives us an approximation to the solution. All right, next point. Let's see, how can I do this so that it fits a little better? There we are. So x0, y0 is 1, 1. Alright, so x1, y1 is 3 halves, 1 half. Y prime is equal to, well, minus y over x. So that's minus 1 half over 3 halves is equal to minus 1/3. x2 is equal to 3 halves plus a half, which is 2. And then y2 is equal to a half plus the slope times delta x. Right, so that's 1 half minus 1/6. 1 half minus 1/6. So that's 3/6 minus a 6 is 2/6. So that's 1/3. So x2, y2 is equal to 2, 1/3. Okay, so there's 1 half, 1/3 would be, oh, about here. So there's my point. And we connect these via a straight line. All right, next point. x2, y2 is equal to 2 comma 1/3. Y prime is equal to minus y over x. So it's minus 1/3 over 2, which is minus a sixth. x3 is equal to, well, 2 plus a half, which is 5 halves. And then y3 is equal to 1/3 plus the slope times delta x. So it's 1/3 minus 1/12. Right, so that is going to be 4 over 12 minus 1 over 12, which is 3 over 12, which is a quarter. Right, so that's a quarter. So that's right here. And then we'll connect that via a straight line. And there's the next iteration in approximating a solution. It's not too good there. Let's try it again. All right, last one. So x2 or x3, yeah, so this was x3, y3 is equal to 5 halves, 1/4. So x4, well, first of all, y prime is equal to minus a fourth over 5 halves. So that is minus 1/10. x4 is equal to 5 halves plus a half, which is 3. And then y4 is equal to y3, which is a quarter, plus the slope times delta x. So 1/4 minus 1/20. So this is 5 minus 1 over 20, which is 4 over 20, which is 1/5. Right, so that's 1/5. So 1/5, right about here, say. And here's the next line. Right, and those lines are flattening out, as you can see. Okay, so that's the approximated solution. Let's compare to an actual solution. So y equals 1 over x going through the point 1, 1, the initial point. All right, so here's 1, 1. Y equals 1 over x goes through 1, 1, and is a solution to y prime equals minus y over x. So at 3/2, we have value 2/3. So we're right there. 2/3, right about there. So that's 3/2, 2/3. And then at 2, right, we're at 2 comma 1/2. At x equal to 5/2, right, 5/2, we're at 2/5, which is 0.4. 0.4 being, I don't know, up here or something like that. And at 3, we're at 3 comma 1/3, which is all the way up here. So as you can see, right, the actual solution, the error gets larger as you get further away from your initial point. Almost got it. Bing, bing, bing. There we go. All right, so the error grows of the approximated solution grows as iterations go on. Right? I mean, it doesn't have to. Sometimes you can get lucky, but here the error is growing. Okay. Right, and you'll see why that error grows. I mean, here's y equals 1 over x, right? And the slope at any given point is here. It is underneath. That's concave up. So the tangent line is underneath it. So when you use that tangent line to approximate the next point, it's underneath the curve. And then you use the tangent line again to approximate, and you're underneath the curve. Right? So you keep shifting the curve, but yet keep undershooting it. So that's what you get. But anyway, I mean, it's really simple. It's a very simple idea, and it does give you an approximation, which is pretty good for, you know, for really tiny variations around the initial point. Okay? All right, so that's the lecture for this section.